In this video, we're going to walk through the solution to a practice problem. Hopefully, you've had a chance to try it out. It's asking us to calculate the number of moles of helium gas that will be required to fill a balloon that's at room temperature and atmospheric pressure if that balloon volume is 7.95 liters. Okay. So whenever I read problems like this, I personally have a hard time processing information in a word problem, and it helps to highlight the information given and then list it out to see how to solve the problem. So I know I have a temperature of 298 Kelvin. I know I have a pressure of 0.95 atmospheres, and I have a volume of 7.95 liters, and I'm being asked about the number of moles. So that's kind of the goal of my calculation, which is abbreviated N, and I have no idea what it is. So looking at these variables, I can now connect them to different equations I've seen. And I've seen temperature, pressure, and volume in the combined gas law. I've seen them in various combinations in the individual gas laws, but none of those include the number of moles. And the only one that does is the ideal gas law. And so I'm looking to calculate this N. And anytime a problem either gives you the number of moles or asks you to find the number of moles or something related to that, like mass or molar mass, then we're going to need to use the ideal gas law. So I'm going to solve for N, and I can rearrange this equation now that it's all variables, or I can do it later as I solve it once I plug in numbers. If I want to rearrange now, I'll have our number of moles is equal to pressure times volume divided by RT. Or I could just plug in the way I have it originally. But looking at this equation, I've got pressure, I've got volume, I want to know moles, and I've got temperature, but I don't have R in the problem. And that is because R is a constant that you're just going to be expected to know, or know that it's something you can go look up. And R has a number of values associated with depending on its units. It's all the same number, just converted into different units. So it's 0.0821 liters times atmospheres divided by moles Kelvin. And this right here, these are the units, not the equation itself, which is an easy mistake to make. Another version of this is 62.4 liters times millimeters of mercury divided by mole Kelvin. And you can see the difference between these two is the pressure unit. And so you want to choose a R value that matches the units of pressure you're calculating or that you are given. And we've been given units of atmospheres. So I'm going to make sure that we use 0.0821 for our R value when we calculate N. So now that I have that figured out, it's really about plugging these values into our equation and then solving it algebraically. So so let's plug in here. We've got a pressure of 0.95 atmospheres, a volume of 7.95 liters. That's equal to the N we want to calculate, times our R value that we've chosen, 0.0821 liters times atmospheres divided by moles times Kelvin, and our temperature of 298 Kelvin at room temperature. So now my goal is to solve for N, which means I need to isolate it. And I'm going to do that by dividing both sides, I'll switch colors here, by this R and T value, so that way they'll cancel out on this side. Oops, 2-1. Remember, algebraically, I can do anything I want as long as I do it to both sides of this equation. All right, and so now I'm going to be able to see that these R values on the right-hand side of the equation will cancel out, as well as the temperature value. And now I have this expression that I can plug into my calculator, and I'll get a number that equals N. And so plugging this all into my calculator, I'm going to get a value that is 0. 0.30896, and it keeps going. And my units here, I'm going to take all of these units and combine them. So I have at the top, I have atmospheres times liters. And below that, I have liters times atmospheres divided by moles times Kelvin on the bottom. And looking at this, I can see a few things cancel out as well. My Kelvin cancel out, my liters cancel out, and my atmospheres cancel out, leaving me with units that are 1 divided by moles, which is the same thing as saying moles. The inverse of moles is just moles. And so I'm also going to now round this off. And I'm not given enough information to know if these are measured values or not, but let's just assume they're all measured values. If so, I have 0.95 atmospheres is our smallest number of significant figures if these are all measured. And so I'm going to report this to 2 significant figures as well. So 0.31 moles is my final answer.